Alright, welcome back to another session on Croof. So last time we were able to evaluate more complicated expressions, and by complicated I mean we have multiple quantifiers, we have some function definitions, and then we have our expression. And that's something we couldn't do before. We were able to only evaluate expressions. Now we are able to have statements and then the expression, which I think it's kind of cool because you can have more complicated things at this point, like maybe comparisons and stuff, like some rules before you evaluate a thing. Because if you think about math problems, you sometimes have some constraints. You don't have just 1+1. It happens to have some constraints and then your question. So that's kind of how this works. And yeah, we have like a small stdlib with basic operators, basic functions. We also have some built-in functions and I guess implications, I call them, these arrows. So yeah, I think it's a good starting point maybe to try and build a CLI. I mean, it's, this is a CLI tool, but I mean an interactive mode. So somewhere you could add something like a -i flag for interactive. And let's say that this would start the Croof interpreter or whatever, like the Croof CLI tool in interactive mode. So you could actually type things in the terminal and try to evaluate things manually instead of letting the current solver do it for you. So maybe it's gonna be like a assistant in proving some expressions or evaluating them. I think that's gonna be kind of cool because for certain problems, like let's say 0.4, it's quite slow. For instance, here it's computing the 5th Fibonacci number, and I'm pretty sure doing it with this solver is easier than doing it by hand, but maybe it's not. We'll see. So yeah, let's go ahead and try to add this functionality. I think it should be kind of interesting. So right now, how this thing works is we read some arguments, right? We have these command line arguments. We are using clap, clap, and yeah, basically here we just display the tokens if you want to use the lexer only. Then here we iterate through the files. So I would still keep some files here because maybe you want to start in interactive mode but load stdlib because you want to have plus, minus, those kind of operators available. I think that's okay. So I think how this thing will work is this thing will stay the same. So we are gonna read the files, right, parse them into an AST. Then we have to type check that AST because we want to make sure that the stdlib works properly, obviously. So we still have to do type checking. Then I guess I'm still gonna keep the solver in here. But now that's interesting. So if you are using -i, so interactive mode, I would still keep the solver because why not? And I guess we should have an extra argument. So if args.interactive, we are gonna do something different here. We don't have interactive yet, so let's add this thing. So here, run in interactive mode. Okay. So in interactive mode, I'm guessing we are gonna have a loop. Right, it's gonna be a loop while true. I'm not sure I want anything else. And we need a way to input from stdin at this point, right? Okay, so we have something like that in utils, right? We have read input, and here you can actually read from stdin. So I might want to make this one public or something, because right now it's only here, but we'll see. I guess we could just copy paste this stuff to read from stdin, but yeah, we'll see. So although thing is, we could just use something like a source map. Right, yeah, I mean, we could just use a source map. So let's use this thing. So if we run it in interactive mode, we can just create a source map. And here, if we pass none instead of the file name, it's gonna use stdin. Interesting, so it doesn't like that, because it expects, even though it expects an option, it doesn't know what it's there. So we should use string like that, even though it's weird, but do I really have to? Yeah, I do. Whatever. So this gives us a lexer for stdin. Now, honestly, that's kind of, I mean, that's a bit annoying, because I don't actually want to read Croof code from stdin. I want to read in a different kind of format. So maybe it's okay. I mean, I guess we could just run it with -i like this, and now it's gonna stay in a loop. So here I was thinking that maybe, yeah, you want to write things in Croof like this or something, and your usual eval, and maybe, I guess, using a dot to indicate that it's done, and then you would use a lexer to parse only this string from stdin, right? And maybe we would have some things like question mark to show you all of the implications. Then you would use numbers to choose one implication to use, and stuff like that. So I think I just want to read like that. Okay, I think that's okay, maybe. But then if I have evaluate, I guess it doesn't matter. We just know it's evaluate, right, in interactive mode. So I think that's fine. Okay. So let's read the line by line from util. Can we just read line? How can we read only one line? So for line, I guess that's fine if we call dot lines on something, and then we do some mapping. Because we could call, I guess, read to string. this just gives me U size. I don't want to do it like that. I want it to be from stdin. Yeah, maybe something like this should be fine. So instead of doing a straight up loop, we could just go through the lines like this. Maybe let's just import stuff. What? stdin. Anyway, and I guess here it wants something buffered. Okay, and here we are gonna get a line. Right. Interesting how it's, I mean, we could call unwrap on that thing, but Jesus. Okay, anyway. So if I do for, I guess that's kind of not a thing. Right, so maybe we could just if let okay line is equal to line, then we're gonna do something with this string. I guess maybe even like this, and then in case it's an error we could just break, right, and we get the line. And at this point maybe I want to have like a let mutable buffer as a new string, and as I said here, while we read lines, we read until a dot. I mean, that's what I want to do. That's gonna make it the simplest way, I guess. So if we find a dot, then maybe we just want to stop. Let's do it like this. What would happen if we do loop this, then we say if line is equal to dot, then we break from this thing, and then we print ln something like okay, just for the memes. Let's see how this one works. So if I give it a dot, okay, nice, so it just goes back. Perfect. So here we can have some mappings with stuff. Okay, interesting. Right, so I would do something like maybe match line. Can I have something like dot? We are doing a to do, then question mark, it's also to do, and anything else we are going to, so it doesn't like that, maybe I have to do as ref or as str. Okay, so it's gonna say what to do. Perfect. So as I said, if it's a dot, then we should parse the buffer. That's my idea. Right, we should just try to parse this buffer. And when it's anything else, for instance, although, yeah, fair enough. If line is equal to dot, then we just break. It's gonna be like a sequential thing. So you give it some lines with Croof code, then you use a dot, it stops, then it parses the buffer, which here we have to do buffer dot push str, and then we give it the line. Right, so here at this point we should have we should have a buffer. So you can think that, well, we're gonna eval 1 plus 1 and then a dot. It's gonna give us the Croof code back. So at this point, as I said, I should create a lexer. Do we have a new? We have a new with a source file. So source file. Thing. So maybe I just want here when we say add file, what if instead we do something like add content? Like create a new function, add content. Content is gonna be s. We're gonna have immutable self, and then we just give it content s. I don't think it's gonna give a result. I think it's just lexer where s into string. And why I would like to do it like this is because when we do add file, we do it on the source map. So we just create a new file for reporting errors. I think that's fine. So add content. All right. So let's get an ID. Let's get an ID. Then for the file name, I guess we don't have one. So let's do it like this. We are gonna have content. We already have the content. That's perfect. So here we call into. And the name of the file is gonna be probably stdin, I guess. I think that's fine. Okay, so it's gonna be like stdin or something. Okay, so at this point we should be able to say source map dot add content, and for the content we are gonna use maybe just reference to buffer. And this is gonna give us a lexer. Perfect. So after we create a lexer, we should run the parser. just like we did there. So we create a parser, we parse. We should merge the AST, I think. So we should still run AST merge because we want the AST from the stdlib to be available for our small program. I mean, program, but it's like small program. Okay, and then we say fail to parse file, fail to parse content. And I don't think we print anything. Fail to parse content. And I mean, we should be able to display the error with the source map now. And we just exit. Should we exit? Or should we just continue the loop? So go back to the beginning because, well, even if you failed, you can still just continue and try again. I think that's fine. Maybe we want to pull all of this thing in a separate function at some point, but yeah. Okay, anyway, so I think that's okay. Maybe we could print the AST just to see it. So at this point, if we run it like this, and we do, oops, let me just eval1 plus 1 dot, we should see the entire stdlib and our eval here. I think that's fine. Nice. So what would be the next step? Well, we have to type check the AST. And maybe like this. Okay, so let's go here. So we create a type checker, we check the program, and here it's interesting. We recheck the old stuff. So maybe we want to optimize the type checker to skip everything that was already checked. All right, and here we should just maybe continue if we get an error. Right, I was just thinking maybe again we could pull all of this stuff in a separate function, but whatever. So here check program goes through all of these things, check define, check implication. It extends with the built-in implications, which kind of sucks because I don't want to do that. Like multiple times. Okay, check define. That's kind of interesting. I mean, for check implications and stuff, check statement, right? Check relation. Well, I mean, I'm not sure. Maybe we could do it here for expressions. Like if the expression already has a type, we can just return the type instead of calling this. But yeah, like something like if expression dot node type, so this returns an option. So if let some node type is equal to this, we can just return I mean, we should, well, node type, some node type, right? So if we have, and obviously empty backup errors. So maybe something like this would help a little bit. But yeah, obviously here we are adding the built-in implications again, which is kind of maybe I want to do this stuff outside of check program, but yeah, I mean, we could do it outside of check program because it's not really checking the program but modifying it. So let's say here we could just do ast implications extend, oops, and we just add the built-in implications. But this guy should be maybe somewhere else. I don't know where though. Right. So yeah. I mean, let's just make it pub function and let's add it in here. Built-in implications, whatever. So now we just add the implications here once. Okay, fair enough. I mean, it's a bit more optimized like this. It's whatever. So I guess if I run it with 0, 1, it should still work, right? With dash I, if we do eval 1 plus 1, looks like it works, right? We didn't see anything, so maybe we have to print something at the end. So in here, print ln, let's keep the okay there, just in case. So if I do eval 1 plus 1 and then a dot, it's gonna be okay. If I do eval a plus 1, it's gonna say binding a is not defined, and then it doesn't know how to add something with n, which is fair. Okay, perfect. So after we type checked and merged the AST, usually we would just call the solver. Right, and I mean we could do this one just for the time being, just to see an example of how this would work. So we create an AST or an A star solver with the implications that we just type checked and generated in the AST, and then we get all the evaluations. Now what I kind of don't like is that it iterates the AST evaluations. I want to iterate just the program evaluations. So here maybe instead of this match, we have to do something like if, no, let okay program is equal to this thing, else we show the error. I mean, it doesn't really work. It's kind of annoying. I mean, we could use something like let program is equal to this thing dot okay or else, and it still gives me a result tf. How do you actually do this one? So in case we get the parser, I want to do this thing, or I guess I want to return the program. Otherwise, I want to do this stuff on the error. So maybe I can just do map. Map, okay. Usually you do or else for something, but this returns result. Unwrap or else. Unwrap or else. Huh. Then or, because map or doesn't really help me. Map or else. Unpack a success. So this applying fallback function. Yeah, but map error. This function can be used to pass through a successful result. Yeah, like I cannot say program is equal to and then program, like that's not gonna work. I guess I have to clone it. Oh, interesting. So I guess this works just because here we have a continue. Okay, fair enough. So I can just have the program evaluations here. Right, so this should still work just like before. We are just being able to do eval 1 plus 1 dot. Really? No solution was found. What? But here it's I guess, no, because we added the built-in implications. So why is that? Instead of solve a star. It's weird for s in substitutions. Really nothing. That's completely weird. No. 0. But why though? Println implication. And multiple implications, but why isn't there, I guess, the built-in ones, right? We don't have the built-in ones, maybe? st. But we append the built-in implications. That's weird. Let me just see here the built-in implications, I guess. I mean, I still don't see them. It's weird. I mean, I guess, yeah, we have them. I just don't see them, right? They were at the end. Yeah, it's here. Okay, that's interesting. So why doesn't it work then? The fuck? Because it's literally here. Substitutions. Well, I guess the main reason would be because here we are cloning the program, right? Then when we are running type check, we are type checking the AST, which contains program but it's cloned, and then we iterate the evaluations from the program, and those evaluations are going to be different than the ones that were type checked because they are not going to have the same types on them. So that would be the main reason, I guess, is because they don't have types. But then that's a good question. In a check program, how can we check the evaluations unless we make it public function? Check evaluation. Okay, fair enough. We just make it public. And we don't create a new type checker, I guess. Right, we just reuse the existing type checker. And we check evaluation. And then it doesn't even matter to merge the AST. We just care that it's a program or not. So we check evaluation. Yeah, but it could contain more stuff. So let's still merge it with program clone. And I think we still have to do check program because it might change. Yeah, but that's annoying. The main reason is program is not going to contain only evaluations. Maybe it's going to contain other stuff as well. We could keep something like let index is equal to 0 or something. Or I guess ast.evaluations.length, so we know where to start. I mean, it is what it is. And in here we are going to not need a program anymore because that's a bad idea apparently. But we are gonna do that. Nice. And here we can do AST evaluations. Can we slice? Can we index? Okay, that looks promising. So we do that. And then index should actually be mutable. All right, and we reset it. Okay, so let's see now. So if we do eval1 plus 1, operator is already defined. So that was the other issue that I was thinking about, is that if we do check program, here we do check define, and if we run check define, how can we tell that we already checked something? I mean, the thing is that the type checker should contain, where is the type checker? It should contain this mapping. So I don't think I need to actually merge the AST then. Let's just try to just have a program. And what if we just type check the program itself? All right. Since we already have all the mappings, maybe we don't even need to merge the ASTs. Maybe it's already in the context of the type checker. Okay, fair enough. That if this works, it works. Fine. Okay. So do we have any printlns? No. Yeah, we have this print here, which I don't like. So 1 + 1. Okay, so now it works in like interactive mode, but it's just for it's still using the solver. Okay. So what should we do next? So here we read the code until dot. I mean, until the line is equal to a dot. Yeah, nah, whatever. Then we create a lexer, the AST. We type check the AST, and we should create a new kind of solver, I would say. Or something like that. So I guess for each evaluation, what I would like to do instead of actually solving it is to show you a step-by-step kind of solution. So initially you would see the entire thing, the entire evaluation, just like it shows it here, right? Then you should be able to see like a list of implications and choose which one to use. That would be the first step. Choose an implication, and then after you choose an implication, you would see another list that shows you where to apply that implication, because it can be applied in multiple ways, I would assume. So that's what I guess I want to do. So that means for each evaluation, let's check solve A star. I guess we need something similar to A star solver. Let's let's see. Conditions. So this one, the first step in substitutions, it would go through the conditions and it tries to substitute the expression with the condition. Interesting. Let's not focus on this part for the moment. I think I just want to focus on this one, and then we'll see. So again, maybe just iterate through all the implications, all of these things, do the substitute using the matcher. Then maybe this part right here, which requires a proof, we can skip for now as well, let's say, and we just push the substitution. Or if it needs any proof steps, we can see. But yeah, we can just push the substitution. Okay, let's try to do this. So we basically need the matcher. Okay. And in here, I'm gonna do the following. So for evaluation, I need something like for I guess after we type check the program, we can merge it, because why not? st.merge program.clone, right? Because now we can just for implication in lst.implications, we are gonna do something. Okay. And then we also have for each conclusion, because we can have multiple conclusions. We are gonna have multiple substitutions and steps that we might need to solve. Okay, let's put also this for loop. Wait, what? So this is gonna be the matcher. Here it's expression, but it should be like evaluation.expression. And we get the new expression and the steps that we need to prove. I said that maybe we just ignore those steps for now. And we are just going to do something like this. But we don't have substitutions, so let's create let substitutions mutable. And I think I want to create a hash map. And this hash map should go from maybe implication node to a vec of expressions. Wait, what? Hash map. Okay. How do I set type? Expression no. Okay. So this is going to be substitutions. Do we have an example with entry? We do. So we have an entry, substitutions, application. So implication node needs hash. I think it's fine. To have hash on this thing. Node. And this one kind of doesn't work with hash, so yeah. Okay, fair enough. So we cannot really have hash. Well, I mean, we could, because here we can just implement. So I guess we could just implement hash for built-in node. Don't we have implement hash? Yeah, we do. So here I'm gonna say display. Fuck. Display hash state. Nice. So this is fine. So now we can just have this kind of hash map. Perfect. Okay, so we get but why doesn't it show me anything here? It's weird. So relation kind doesn't have hash. Nothing. And it's still complaining about something. Entry exists for, but it's not satisfied. Implication node still doesn't have hash. Really? Then we can just add it. Expected whatever, found whatever. Okay. So E now is something like that. So insert wants a value. Don't we have entry? I do it last hash map value back. No. Substitutions dot. I mean, entry, I knew it was kind of useful. So if there isn't anything, I guess we should just insert. Okay. So insert it wants just the value, so I should do something like vec substituted. Otherwise we can just say substitutions. Can I just implication clone dot push or something? Here it's fine. Get mute. I'm pretty sure there is occupied. What if we do occupied e dot get mute dot push? Well, I guess we could just do a match on this thing to make it easier. So if we have occupied versus vacant, we do something like this, and otherwise we do this. Okay. What? Interesting. So this is gonna create this kind of substitutions mapping, which is something that we need. And after this entire for loop, what I would like to do is maybe for to iterate them, right? So for implication and substitutions, iter. I guess I could just do that. And would this give me? Yeah, it gives me them. So let's print the line. Let's print the implication for now. So this should show us, or I guess give us, the implications that we can use for evaluating this expression 1 plus 1. So we can apply this one, we can try this one, and we can also try this one. I think that's cool. So the next step would be giving you the option to choose one. So maybe we are gonna put a number in front of them and hit a message with like choose which implication to use or something. I think that's what I want to do there. So again, we read the input, we parse type check, do all of that, then we generate some substitutions. Right, we display them, print ln available applications, let's say, and if we also enumerate this thing, we should get an index and that. So this should be something like maybe parentheses, maybe just semicolon, just so, print ln, which application do you want to choose? Maybe it's just print, right, with it reading from there. Okay. Now we just need to read one line, I guess. Let's see. And I'm just thinking if this can be refactored in a better way. Not exactly sure. Not exactly sure. Maybe in a separate function, but I don't see really. Maybe this entire algorithm will be interesting to try to do something about it. Like, let's say for instance you realize you chose the wrong implication and you want to go back, so you are allowed to say something like return or something like go back. So then we need to keep track of the past expressions so you can undo, I guess. Which implication do you want to choose? Okay, so we just have to do something like this. Lines, I guess. A read line. A read line gives you just a single line. Lines. Can I do next? Let's think about it. So if you don't get a next, then it kind of doesn't work. So maybe I should just unwrap this call. Unwrap, right? Makes sense. Or maybe just let some choice is equal to that, else we just break, my opinion. Oh, let okay. Wait, what? It returns option result. I guess so. Can I do something like that? Okay. Interesting. So now I would also want to parse this thing, maybe. There's a parse. Now hopefully this keeps the same order. So let's parse u size. Wait, what? Else break, obviously. So now we have the choice as a use size. And can I do something like let application substitutions is equal to substitutions iter. Can I just index? I mean, I could just have mapping is equal to vec and maybe something like mapping I don't know if I want to do it like that. It's really not an option to have something like items or something. Iter collect and then we call choice. I guess. And then maybe we want to print this again just to make sure that we get the same values. But yeah, I mean, we don't even need it to be a hash map after we make it. So we could just do let substitutions is equal to this thing, right? And then it's fine here, and then we are sure it's gonna be the same. So eval 1 plus 1, and then it asks us for which one to use. I know that 2 is gonna be the one to use. Wait. So can I flush? IO std out flush. What? Whatever. So we eval 1 plus 1 dot, and then it asks us which one to use, 2, and then it should apply it, right? Or I guess it should ask us which substitution to choose. So available substitutions, and then for I substitution in substitutions.iter.enumerate, it should do something like this: I substitution, and then the same thing as here. Which substitution do you want to choose? Here the implication, I don't think we are gonna need it anymore. Not sure. Then it gives us the choice. substitutions of choice. I have to clone it, I guess. And this gives me a new expression node. And with that expression node, we should pass it in this. So here let's say expression. Let new expression is equal to evaluation expression. Ah, shit. It's in here. For each expression, then for each implication, for each that. So this substitutions thingy should be inside of here. And I would assume this wants to be some kind of loop. So we get all of this stuff inside of a loop, all the substitutions. So all of this stuff needs to go inside of the loop. Okay, and at the end, expression is equal to that. Really? Because this needs to be outside. And I think this one as well. No, this one is fine here. So again, it's I guess I need to clone it or something. Okay. So for each evaluation that we have in our stdin program, we create the substitutions, all of them, right? Using our matcher. Then we say, okay, these are the available ones that yield some results. Which one do you want to choose? Then it shows us the possible substitutions. We choose one, and then we move on with that next expression. So yeah, let's try to run it. So we evaluate 1 plus 1, and here it's gonna say, okay, which one do you want to choose? Let's say we want to choose 1. Which substitution? Doesn't really matter, it's kind of the same thing. Let's use 0. At this point, obviously, there are gonna be a lot more. So we went with this one, and we could use this one, for instance. Let's keep it with natural numbers though. Let's use 4, and we are gonna go with the only possible. I mean, I guess if it's only 1, it could just auto apply it, but yeah. Okay, here we should search for 0. This is the identity one, so let's use 0, first one, and then we are gonna use this built-in one, so 0. And I guess at this point it's done. So how can we stop here? Maybe by doing a dot or something. Which implication do you want to choose? And I guess here if choice is equal to dot, maybe we want to also println solving for, or I guess just printing the expression should be enough, or maybe eval. Anyway, so here if we get a dot in here, we might want to just stop. So println finished, or I guess done, and maybe break from this loop and move to the next evaluation. That's fine. Done, and maybe also println the expression just to see it, or done and then show the expression. Why not? So let's see this again. Eval 1 plus 1. So let's say we use 1, 0, I think 2, 0, and then we have, I mean, it's annoying that it's not sorting them, but over on that, and then 0, 0, and then we stop. So done 2. And I guess we could have even more complicated things, like what if we have for all A in N, for all B in N, and we want to evaluate, I guess, A plus B and dot. Wait, we could use this one? Wait, why is it on the same first expression? Interesting, so it's why did it go from the beginning though? Why did it go from the beginning? So we read one here. Because we never cleared the buffer. So I should say here buffer is equal to string new. Like that. Eval all A in N. Let's try to solve a more complicated one. For all B in N, let's do A plus B squared. So what can we use here? Available implications. That's with booleans. I mean, this won't work though. I guess I don't have the other thingy. I guess just doing that. Okay, fair enough. Wait, in stdlib. I mean, we have exponentiation of natural numbers. Okay, fair enough. Let's try again. Exponentiation. So if I do RL wrap, I don't have it. Sad. Eval for all a in n, for all b in n. Let's try to solve a plus b squared. So this is the actual first try. So choose a dot. I guess first step is to convert the two into this kind of successor thingy. I guess another subcommand which could be cool would be like a question mark to show you all the implications, because maybe you don't want to go in the file and search for them. But I think this is better to show you the ones that work. I don't know. So the thing is, we want the exponent to look like successor b, right? So that's why I'm gonna apply 4. Let's apply 4. And we're gonna change it to this, change it to this. So AB, and the exponent is successor 1. Let's look for some exponent stuff. So this one looks like a good formula to apply because it's gonna simplify everything. So let's apply 6. And we're gonna get that. So it's 0. Now I want to apply something with exponent 1. So get rid of power 1. So let's apply 3. 0, obviously. So we get this stuff. I would like to get rid of the parentheses from here. So let's apply 2. And we are gonna go with 0. I mean, parentheses doesn't really matter in this language because it's like an AST anyways, but you don't see the AST, so it's good to use parentheses. But yeah. The next one I would like to use is maybe like something like this. Opening the, distributing the first term on the second one. So let's use 0. And we are gonna do it like this. So we got this entire stuff. Okay, nice. I would say that we want to use a times b equals b times a, right, to swap them around. So let's use 0 on the first item. And now we can use distributive stuff again. So let's use 0 again. So we get a times a plus a times b, so on, right? Now I would like to use it on this one and swap it. So let's do a times b equals b times a again, so 7. And I want the second one, so 2. And now let's distribute it again, so 0, 0, the only available one. Okay, so at this point we are getting closer. I would maybe open the parentheses from here and here, here and here, pretty much everywhere. So let's apply 6. Yeah, again, it's annoying that it swaps them, but let's apply 5 until we are done with parentheses. So it's 2 on 0. Now it's 5, again annoying, on 0. Now it's 0, we apply it on 0. Now it's 6, oh, and we apply it on 0. So we got this stuff. Nice. Sadly, we don't have stuff like a plus b equals to a or something, but maybe we do. Let's swap these two around. So let's use 1 on which one? On 2. Yeah, we don't really have a plus a equals to a, let's say. So we have stuff like this, but we don't have the reverse of this formula. Or I guess more important would be, which one? Yeah, I guess this one. We don't have the reverse, which kind of sucks. Yeah, that would be kind of useful. But I mean, I think it's good enough. Sure, what we could do is say, okay, we are done for now. Okay, so we are done with, we got to this thing. And what if we are trying to say something like, okay, I would need error wrap. So let's go to the next flake and let's add read line wrap. Or is it not readline wrap? It is. So if we do error wrap on this thing, readline wrap, we should be able to say, okay, we got to this point. What if we are trying to do something like this? So distributivity, but the other way around, right? So what if you can do b plus c? So we parse this thing, we just parsed it. Let's continue with evaluating this, right? So we do eval that, boom, binding a, okay, so we need to do for all a in n, for all b in n. Let's continue, right? So interesting, but we don't have, why isn't this one available? Maybe because we don't have parentheses. I guess so. Maybe it's because we don't have parentheses. So let's say for all a in n, a is equal to a with parentheses, right? So we just add the option to do parentheses. So let's use for, and let's add parentheses to well, yeah, it's a problem because this one is different maybe than the other one that we were solving, right? Let's do a wrap again. Let's include this one. And the main reason why is because we don't have operator precedence. We just take them in order. So we should have kept it like this. and then continue with solving it. So this expression was different than the one that we last got. This isn't gonna work because we don't have for all and for all b in n. Okay, nice. So let's try it, and now we should have, wait, we don't. Maybe if we swap them. Maybe if we use like 5 or something, and we get them in front like this, like 2. Doesn't look like we have, but why? If I do a times b, a times b plus a times b, here it works. Alright, but why didn't it work for this one? It's an interesting question. Maybe what I want to add is go back to this thing for all n, and we want to allow this parenthesis to exist. Okay, let's try. So if I parenthesize this expression, maybe it's gonna work. Let's see. So if we use 5 and we add parentheses, let's do 17, an idea, 17, and let's do 0 again. Is it gonna add parentheses around? No, it's only around this. But I would like to have parentheses around this entire thing. But how is this one different than this one? I don't see it. Right, it's the same thing. The fuck? Or am I blind? Yeah, I guess it's the same thing. What the fuck? Anyway. Let's try it again. So maybe just the last one, but I want to use the natural numbers one. So 3. What if I move them at the end? Let's use 1. Let's do 4. So this one with both of them at the end. And now let's add parentheses. 6. and this one's not what I wanted. Maybe this one, but again it's weird. Parentheses again. And do I have parentheses just for the inner stuff? Doesn't look like I have. The fuck? Yeah. Yeah, maybe being able to cancel one of these and go back to choosing an implication because you don't like the options. That would also be a thing. Maybe we need to apply 0 a couple of times, like bringing it to the front like this, and then applying parentheses or something. Oh, what's this one? Looks interesting. Parentheses plus C. Oh, this one could work. This would add parentheses. So if you think about it, we have A plus B and then plus C. Let's try 5. Let's see what happens. Yeah, so we got, I moved B, A plus B here. Oh yeah, I mean, I was right about that, but it's the other way around. Let's do 0. At this point I'm just randomly okay, I don't like that. So it was kind of decent. So I would say we want to move these two to the front and have parentheses around them. That would be the goal. So maybe if we use swap, then have like a 2. So we have basically, this is the left hand side of the tree and this is the right hand side of the tree. That's the idea. Then this is the right hand side of that and the, I guess, left hand side of that, and then the right hand side of that again. So if we just add parentheses to that, maybe, so like a 0, and we add parentheses to this. Now this one, wait, where is the fuck? This, just that? It's so weird. I kind of want... Oh, actually, maybe this one is finally gonna work. It didn't really work. Why though? We might want to swap them. Let's do 7, 2, 7 and 2. This could work again, but this is the B term. So what if I want to swap this with a B term? So we can do something like 6. Six, 1. And then maybe again, like 1. If we get AB here, that's good. So 0. And then 3. If we try to parenthesize with 2, should we finally get that we don't get the AB stuff? That's so annoying. But why are these two the same though? That's a good question. We get this one. So do you want me to swap? Okay, let's try to maybe swap them. So we'll continue from here. For all A and all N. That. Fuck. Ah. We have eval twice. So if I try to swap this one somehow with this one and then that one, let's do 2. Oh, straight up just swap them. Okay. And then if we try to apply parentheses, do we finally get that? I think so. I think it's 12. And now we should have finally this this formula for. So we get something that's pretty close, like it's closer to what we wanted. A times A plus this one plus B times B. Let's define some stuff like for all A in N, A times A is equal to A squared. And maybe for all A in N, A plus A is equal to 2 times A. And now we can resume to evaluating our expression. And that, and now we can apply 7, for instance, on 0. We might be able to apply that formula again. Now a plus a, 5. Go on 2. We got this one. I would like to open basically the parentheses to this. So it's gonna be 1. We choose 1. Nice, so we get this. Maybe we can swap this thing around like multiplication style. So 0. Go with 1. And maybe just the last thing would be to open this with this parenthesis. So I guess it's 8 in this case. And 3. So if we look at the result, it's a squared plus 2. I mean, it's 2ba, but whatever. Right, which is kind of cool. So we basically managed to solve a plus b squared, right? And got to this this result, which is kind of cool. Yeah, I guess I think it's fine. Again, the only extra thing I would change maybe in main would be allowing the user to go back, right? Maybe also you don't have to stop this kind of inference. You can just define your own expressions when you need to somehow. Not sure how, but that would be a good idea. Like maybe dot just gets you back into editing mode, and then once you use another dot it brings you back into evaluation mode, but you also need a way to say that you are done and that's the result, right? But yeah, like it's pretty cool. Like it wouldn't be able to figure this one out with the solver, with the A-star solver, because it's very, very slow. Like no way it's able to do something like that, which I think it's fine. Now yeah, what it's left would be here we just take all the substitutions, we don't prove them. So you should see something like, okay, that's a substitution, but you need to prove it. So in something like eval 1 is less than 3, let's say, right? You could just use 2 and you get true, right? But you need to prove this this thing, so that would be left, right? And the proofs, I guess, should be done also by the user similarly. So yeah, but I guess that's all for today. I think I'm happy with the result. Like it looks decent. Obviously I would refactor these things somehow, but I think I'm happy with the sequential prompting. I think that's fine. I don't see another way to do it other than just sequential. And the other thing that would be nice would be to keep the same order of these things somehow again, so that you could just create a proof by using the numbers only, or maybe at the end of evaluation it shows you all the steps that it did. That's also a cool one, because right now if we just run it on 01 examples, it here it shows you the expression and then the steps. So once you hit dot, it shows you the steps that you made and then the result, or something like that. I think that's also a good idea. Yeah, right, maybe, yeah. So yeah, maybe the refactoring will be just moving this entire thing into something like a star solver, and that should be it. So yeah, I guess that's it for today. We'll see what we can do in the future with Croof, but until then, see you.